In this video, I am going to demonstrate a real life example where we will use two different designs to create the experiment. So I'm going to call it hardness testing experiment. Hardness testing machine experiment, right? So hardness testing. What is it doing? There is a machine which has that presses a rod with pointed tip. So it will press a metallic rod with a pointed tip into a metal specimen with a known force. What we are doing here, we are measuring depth of the depression that is caused by that pressure. Depth of depression caused by the tip. Which determines the hardness of a specimen. Which determines the hardness of the specimen. So two different tips are available for this machine, tip 1 and tip 2. And although the precision variability of measurements made by the two tips seem to be same, it is suspected that one tip produces different mean hardness reading than other. So we suspect that one tip produces different mean hardness than other. So an experiment could be performed as follows. A number of metal specimens, for example, let's say we take 20 metal experiments. So we take 20 metal specimens and they could be selected randomly, right? So we take 20 metal specimens selected randomly. Half of these specimens could be tested by tip 1 and the other half could be tested by tip 2. So I have specimen 1, specimen 2, specimen 3. I have 20 of them, right? Or just randomly, I'm going to pick randomly some of them from one, let's say S2, S4, and some, and maybe let's say S10. So there are N1 equal to 10, and then similarly here N2 equal to 10. So this is done randomly. Half of these and these, the ones that came in first sample, we will test by tip 1, tested by tip 1, and these are tested by tip 2, right? So this is an example of completely randomized design. The average hardness of two samples could be compared by using a t-test, the general t-test for difference in means. So what you're going to get is you're going to get tip 1, tip 2. So let's say the first measure of hardness for the first observation in the sample for tip 1 is Y11, then Y12, Y110, and then here you get Y21, Y22, Y210, right? And then you can just use a t-test to compare it. So this is what is called a completely randomized design. This is an example of completely randomized design, or CRD that we call it, right? And we're going to use t-test, or we could use analysis of variance approach to do work on it too. Although since there are only 2 tips, we don't really need ANOVA, but if you want, you can. If there are more than 2 tips, that's when you usually would have used ANOVA, because ANOVA is used to compare multiple groups. So there is no harm in comparing t-test to sample. It's going to give you the same answer as what you get from t-test. But a little reflection will reveal a serious disadvantages in this completely randomized design. Because suppose the metal specimens were cut from different bar stocks that were produced in different heats, or that were not exactly homogeneous in some other way that might affect the hardness. This lack of homogeneity between specimens will contribute to variability of the hardness measurements, and it will tend to inflate the experimental error, thus making a true difference between the tips harder to detect. So to protect against this possibility, we can consider an alternative experimental design. What we can do is we can assume that each specimen is large enough so that 2 hardness determination may be made on it. Right? So for each specimen that you collect, so you collect 10 or 20, whatever number you collect, let's say you just have 10, you will need a smaller sample size also. That's also another advantage. So let's say you have 10 specimen, you use one end for tip 1, the other end for tip two. So the alternative design would consist of dividing each specimen into 2 parts, then randomly assigning one tip to one half of each specimen and the other tip to the remaining half. So what you would get in this is you would have like a specimen. So now you only need 10, and they would actually give you smaller experimental error with a smaller sample size also. So it's good to think before you design your experiment, right? Now you have tip 1 and tip 2. So each specimen you are using is large enough that the 2 hardness determinants can be used by. So this is your specimen. This part you use for tip 1, and this part you can press in the tip 2, and then you can measure that the hardness, right? So this one is giving me y11, y12, y21, y22, yn1, yn2, n being 10 in this case, right? And then what you do is this is what is called matched pair design. There is a t-test for difference in means for this that you can use, or you can write the statistical model as yij equal to mu plus beta j plus epsilon ij, where yij is the observation on hardness for tip I on specimen J. Mu I is the true mean hardness. So this is mu I, and beta J is an effect on the hardness due to jth experiment, is an effect that you're measuring on the hardness due to jth specimen, and epsilon ij is the random experimental error, as always with epsilon ij is the random experimental error with mean 0, variance sigma square. So what we do here is we compared paired differences, di's, d1, d2, so it's basically yn1 minus yn2. Sorry. And rest of it is in your notes. It's mu d equal to 0. You're testing mu d equal to 0 versus mu d not equal to 0, the test statistic is d bar divided by sd over square root of n, where d bar is the mean of this, sd is the standard deviation, so d bar is sum di over n, sd is the standard deviation, which is sum di minus d bar whole square divided by n minus 1. So I will stop here. So this is called paired comparison, and it actually illustrates blocking principle that we will discuss later. It is actually a special case of more general type of design called randomized block design. The term block relatively refers to a relatively homogeneous experimental unit. In our case, metal specimen are their blocks. So these metal specimens, each of them is a block actually. Right? And the blocks represent a restriction on complete randomization because the treatment combinations are only randomized within the block. So we'll talk more about this principle of blocking or pairing. We have effectively lost n minus 1 degrees of freedom here. So this t is going to be, this test statistic is going to follow t with alpha over 2 n minus 1 degrees of freedom. And the rest of the testing, you know how to work with that. So I'm going to stop here, and I'm going to make another video for randomized block design or completely randomized block designs.